So our second speaker is Professor Yuanwei Liu, a full-time professor in Department of Electrical and Electronics Engineering at the University of Hong Kong. Let me introduce him briefly. So he received his PhD degree from Queen Mary University of London in 2016. Prior to joining HKU, Professor Liu was a senior lecturer at Queen Mary University of London and earlier postdoctoral fellow at King's College London. So Professor Liu is an IEEE fellow, AAIA fellow, and a Web of Science highly cited researcher. He currently serves as co-editor-in-chief of IEEE Comm TC newsletter and as an area editor or editor for multiple flagship IEEE journals, including IEEE Transaction on Communications, Transaction on Wireless Communications, and IEEE Communications Survey and Tutorials. So his research interests span wireless communication, signal processing, 6G networks, machine learning, and generative AI. He is a recipient of numerous prestigious awards, including the IEEE Communication Society, Heinrich Hertz Award, and the IEEE CommSoc Outstanding Young Researcher Award. So in today's talk, Professor Liu will present pass, lost meter, and near wired communications, focusing on pinching beamforming, practical system architecture, and open challenges for future 6G networks. So let's welcome Professor Yuanwei Liu for his talk.
Great. Yeah. Okay. So thanks, Lex, Kashev, for your kind of introduction. Yeah. So I'm very excited to be here, right? So when I landed in Kaohsiung, right, I feel that everywhere is very spacious and we have good sunshine, right? So people here are very peaceful, right? And very spacious, right? You know, previously I was living in London for 11 years. Then I relocated to Hong Kong to last year, right? So this is more like, yeah, so I'm from a very tight place to a tighter place, right? So that's why I feel very like nice here, right? It's just like to enjoy this like good campus, and so it's in the mountain near the beach. Wow. So it's fantastic. Okay. So let's come back to our talk, right? So today I'm going to talk about the pinch antenna system, the past. Yeah. So I trust that Zhigu yesterday has introduced some basic concepts and also with some his design. Yeah. Now let's see what is my perspective, right? So this is today's of my outline. So if you are familiar with my research style, usually I will talk about from three perspective, right? So basic case study and the research challenges, right? And for the past basis, so usually we will talk about from what is past, why do we need past, and how to implement past, right? So I give this a name, right? So you know, so my unique advantage is to give some different a good name to easy to pronounce, like star, like the nice, near field sensing, right? And also for this kind of pass, and also something this kind of thing, yeah. So now let's see. Start with so what is the overview? Start with the prototype, right? So now actually we are on the road to the flexible antenna system, right? So what is flexible antenna system? Yeah, we give this, for example, we enable the active reconfiguration of the channel parameters to boost the performance. And then we can adjust their positions, apertures, and the electromagnetic properties to make it. This is the thing. But the road is already very crowded, right? We have a lot of fantastic designs, right? So for example, the red star, right? For myself, I'm also actively pushing this kind of stuff. And we have the fluid antenna, we have mobile antenna, we have dynamic meta-service antenna, we have reconfigurable holographic surface, we have a continuous array kappa. This is also another direction I'm pushing, right? So you may ask me that, why do you need this kind of path? So what's the advantage, right? Let's realize this gradually, right? Okay, now let's see what is path, right? So this is a waveguide, right? So I'm very, I trust everyone of us is very familiar about this waveguide, right? And then, but the waveguide is wired communication, right? And we put the pinch here. It's more like antenna, right? so the signals will be readied out. Right? If we put two pinches here, like two antennas, it means that, okay, we will have the double antenna, like the multiplexing or array gain. This is the case. It's like two antennas. Right? So this fantastic area is the first proposed by the Docomo. Right? So if you go back, check my research, a lot of my research are have the relationship with Docomo. For example, Norma, Star, so and also the PASS. So the Docomo people, they developed the first the prototype, right? And actually, yeah. So this is we can see this is the the prototype they have demonstrated. This is the waveguide. This is the waveguide, and this is the pinch. This is the pinch. When we pinch there, and the signals will be read it out, right? So this is the case. If we go further, right? So this is they use this kind of 6 gigahertz band. Right, so we can say, okay, this is this is a transmitter, this is a pinch. We pinch it here. It's more like the antenna, and then the signal will read it out, and the data can be transmitted. And if we remove this pinch, the signals will not be transmitted. Yeah, so this is the case. Right, and if you have a closer look at this pinch, this is a pinch. This is like the plastic thing, and this is the touching point. Yeah, that's it. Quite clear and tidy, right? So usually, I'm like the application-oriented researcher, right? What does that mean? It means that what I want is like my research, the contents can be implemented in the 5 to 10 years, right? If you see that, oh, this idea is fantastic, so it will be implemented in 30 years. Yeah, for me, it's too long, right? So life is short, right? We need to yeah, this is the case, right? And now let's see another thing. So what is from the why pass? So now we need to see what is why do we need the pass, as I say. So compared with the conventional thing, right? So for example, the conventional stars, the conventional the rays, or even the other kappa. So what is the advantage? The first thing is the line of sight creation. So what does that mean? So we know that if we compare, so line of sight is mainly the power, the radiation for the wireless communication, right? So for example, if we compare to line of sight with non-line of sight, so in terms of energy, it's more like the adult is fighting with the child, right? So maybe 95% or maybe 99% of the energy is delivered by this kind of line of sight. But usually we do not see this at line of sight, right? So we are using this our phone to call, to use WeChat, WhatsApp to contact with our friends. But have you seen where is the base station? Right? No, because everything usually is for the non-line of sight, right? But if we can create line of sight, that would be fantastic, right? So this is our main point, yeah. Or this is we want to pass the signals to follow you, right? Or in Chinese, we got the four good characters. It's called 如影随形, right? So this is I trust something maybe can understand me. Yeah, I can. Professor Wang is smiling, so he understand me. So this is the thing. What we want. Wherever you want, you go where, and the signal will follow you, right? So I give you an example, right? So today I'm going to this office, right? But my signal is not that good, right? And then I come over and I sit here and I press the button. Right, and there is a pinching to pinch there, right, and the signal will be serve me, right, and then when I release this button, right, I finish my work, I went out and I release the button, and then the pinching is just it is released. Then no energy will be wasted. So this is what we want to sell, right. Another advantage is that the large scale antenna reconfiguration, right. So I also work a lot for this star, right? So, and for the kappa, so I attack myself is fine, right? So if, for example, if this is like the kappa or this something like a star here, anyway, so if it is blockage, no matter how you adjust this kind of phase or this kind of amplitude, it's always be blocked, right? So because this kind of angle cannot be very much, right? But if this is the path, if it's blocked, right, you just block here, you just activate another pinch antenna in another room. That's it, right? So by doing so, we can achieve 10, even hundreds of meters, a large-scale antenna reconfiguration, right? So this is another advantage of path. The third one I want to say is that, so previously, if you work on the star or work on the kappa, right? So if we implement this antenna, when you finish the implementation, that's it, right? So you can, if you want to add or remove one antenna, it's not possible, right? But with the pinching, it's just a pinch, right? So you can easily to add or remove this thing, right? So in that case, we can make it a very scalable implementation. This is another thing. The fourth thing is near field advantages, right? So I worked a lot for this kind of near field communication, near field sensing, right? And this is fantastic, right? So to be honest, when I started this direction, I never thought it will be like the hot direction, right? So that's because this is initiated by my star, right? So this kind of thing, right? But now near field is very like the popular already is already included in the 3GPP, yeah, standard actually. I just because I'm also an active member of the 3GPP. I'm the representative of Hong Kong U for the 3GPP. I follow this thing. So but people will argue that Yuanwei, yeah, so near field is fantastic. They got a lot of advantages. For example, the trajectory, it can this kind of beam focusing, right? And also it can trace the trajectory of the moving target, like the UAV, like the vehicles, like the. So this is fantastic. Previously, we rely too much on this kind of camera to do this trajectory, or do this kind of GPS, right? So this is so a lot localization, right? Rely on the GPS. But if the GPS is, but if indoor or where a lot of mountains, it's very like inaccurate, right? So its GPS doesn't work, right? So just to give you an example in Hong Kong, so Google Map is not that useful, right? Because sometimes I use the Google Map and just work on there, and then I see this is a position and this is a building, but it's just on top of me. I cannot reach that, and so and then I check the Google Map. It says, oh, it's just there, but you cannot reach. It's because its localization is like not accurate, and you take a taxi and turn like half an hour to reach there. So this is the case, but. With in that case, GPS not that accurate. We do need to use the near field to help us do some localization. Yeah, so this is the case. Yeah, but people will argue that, oh, this near field, we need a large aperture, right? So to realize this kind of near field advantage, because we have this the so-called relay distance, right? But if you see that, oh, in the future this whole world will be like the antenna aperture, no one will believe you, right? So it's not possible, right? But pinching antenna, if you see that, okay, just put the waveguide there, right? Hiding in this kind of thing with like a light strip, people will believe you. It's possible, right? So this is the case. So and another thing I'm pushing at the path is that pinching antenna system path is 100% near field, right? Because it's low. You need to calculate the position from each like the antenna to you. This is the case. Right. Okay, so now we move further. Let's see the kind of the physics and the principle. Yeah. So now let's see. This is a pinch antenna. So waveguide, sorry. So previously, this is our mantle waveguide. So all the waveguides are covered by the mantle. Right? Because this is wired communication. We do not want the signal to be read out. This is the previously, right? But now we want the signals to be read out, right? So it's more like, okay, this is like we want this one to collect on the air. This is what we want, right? Yeah. Another thing I want to emphasize for this near field is that so this kind of line of sight, I can give you an example. For example, I trust some of our boys love playing basketball, right? So and if I can pass the basketball to Professor Wen, so I have several method. For example, I can hit the ball, right, and give you the high curve, direct. So, but the most reliable thing is that I just hold this ball and pass this and hand to hand, Professor. Right. So this is what I want to express. Why we need it. We want to shorter the distance, shorter and increase this kind of line sight. Right. Okay, so let's go back this kind of thing. Okay, now I give you another like the concept. So to realize that, you may see that, oh, Yuanwei, this path is that very commercialized or not, right? So currently, I give you another similar concept, RCX. I just want to show the example. So this is a leaky coaxial cable. Actually, it's extensively used in the mines, railways, subways, tunnels, shopping malls, airports, right? So they are commercialized stuff, right? And actually, London Underground is using this, right? So the difference is that so you can this is LCX, right? So LCX is that okay? So we put this is more like antenna, and then do some punch on this antenna, right? Punch some slots, right? Punch some slot here, right? But if you punch the slots, you cannot make it recover, right? But if you pinch something here, you can remove the pinch, right? So they share the similar concept, but of course you use different materials. This pinch antenna use a waveguide, and then you can regard this LCS as a special case of path, or less flexible. Or in other words, we can regard the pinch antenna path is like the more flexible design for this for this LCX, right? So this is we can give you like the commercial example to say, okay, this is like the application oriented things. Okay, now let's move to my like the research contribution. Yeah, so you will see that, oh, Yuanwei, so it seems that you are not a antenna design guy, you are not like the material guy, right? So you are keeping talking this kind of boring stuff for already like the 10 minutes. So what is your research contribution, right? So now let's try to move to my research contribution, right? So I'm like the modeling guy, I'm like the MIMO guy, I'm like the signal processing guy, right? So now let's see what is the case, right? So see, so actually this is what is different. We need this kind of electromagnetic coupling, right? So okay, we have, if we put this two waveguide close together, right? So the signals will launch something like this, right? So they will have some like the electromagnetic coupling. The signal will jump between these two waveguide, right? Or we call this a power exchange. This is bad, right? So because we do not want the signal to jump between two different waveguides, that's why we put the metal outside, right? So, but the pinching antenna is different, right? So we want to use this kind of the so-called electromagnetic properties. So we can ask these signals from the wired communication to wireless, right? So this is you can see my title is called from the last mile to last meter is something. What does that mean? So in the last several decades, right? So we rely on this kind of optical to communication to indoor, and then use the wireless to serve some like indoor or something like that. So that's why we call it wireless to serve the last mile communication. But the last mile is not enough, right? So it's just like we want to is closer, right? We just want to put the pinch here and service in 1 meter. This is what our like the final goal, right? So this is the case. But how to achieve this? What's the theoretical things behind that? Right? So let's give a closer look on this one. This is signal. So this is now we move to my research contribution. So this is signal, red one, and this is the blue things is like the signals read it out, right? Now we play with the bits like the physics, right, or mathematics, right? So with this kind of Maxwell equations, we play with that. So you know, I love that. So Professor will know this. So previously in the start, I always play this kind of thing, right? So this is one of my unique advantage, right? And then we call this kind of coupling length and the coupling coefficient, right? So this is the thing we need to like the digest. Digest means that okay, we put this thing. This is coupling length. This is basic, right? So if we can just actually, no matter what kind of theory I was using, to the reality, we just need to control this coupling length and spacing. That's it, right? So if I give you another closing, you can see this is a red signal. Red signal. This is for example, this is red signal. It's a wire. This is wireless. Blue signal is wireless. At this point, when the coupling length is 0, all the signals are within the waveguide. Right? And if you increase this kind of coupling length to the 7 millimeters, right? Here is a wire signal is 0, and all the signals are read it out. Right? So 100% wireless. Right? And interestingly, if you increase the coupling length, the wireless signal will be reducing, right? So which means that there is optimal coupling length existing. So this is interesting, right? Another thing is about this spacing, right? Spacing means the distance between this pinch and the waveguide, right? So we can see, okay, so this is like the 2 millimeters. We got very strong coupling length. It's nearly like the good thing, so we can most of the signal can be read out. And this is like the like it's more like releasing, right? Releasing means that all signals are within this like the waveguide. That's it. This is like the basic principle, right? So actually, no matter it is like the pinch, or this is a pusher, or this is like the electronic relay, it all work because the theoretical thing and the behind this is just to control this kind of coupling length spacing. That's it. Right? But I still use the pinch antenna, use the pass because I want to acknowledge originality of the Docomo. So they are they have a group of fantastic guys to do this. Right? Okay, so now we move to this kind of single model. Right? So now hardware model is more or less clear, right? EM wave, this kind of thing. It's more like, now we move to single model, right? So we are like the communication and single processing guy. So what is signal model? To be honest, when I first get in touch this kind of path, I feel very excited. When Zhigu told me this idea last year. So because the basic element is very clear and tidy, right? It's just one waveguide, one pinch. That's it. Right, and just like normal, the basic two-user case is very easy to understand, right? So we worked a lot with that time, so with Octavia as well, so on this normal. But now this like the path, and then you can this is like the Lego, like the basic element. But with this one, you can do different combinations, right? So even do this kind of like the table, a car, or even a city, something like that. So, and the problem I will discuss later. So what sometimes I feel very disappointed, and why is that? Right? So and then so this is like the research is like up and down. It's like your mood, right? So, but sometimes you find something new, right? And compared to existing things, now we have the additional in waveguide propagation. This is the difference. Two main difference. First, they have additional in waveguide propagation compared to the previous wireless. Another thing is that it is 100% near field communication or near field sensing, right? Because this is, we need to calculate not from this point, from every single point. So every single like pinch to the users. That's it. Right? And now we have two models. The first one is equal power model. So what does that mean? Equal power model means that, okay, if you put 4 pinch there, right? And every like the signal from each pinch is 1/4, equally distributed, right? And but in reality, for example, if this is like the power. Assume that it's a power to transmit here, and we have multiple pinch. So if all the pinches are the same, right? Just a pinch or not, we just consider the simplest case. This one should be 1/2. I just assume this is a 1/2, right? And the second one should be 1/4, right? Because this should be half of this signal. The third one should be 1/8, right? So this should be the proportion, right? Of course, we can argue that Yuanwei. Of course, we can achieve this kind of equal power model. Yes, theoretically speaking, yes, but in reality, it's difficult. So why is that? Because I have mentioned that. So if we want to do that, we need to accurately control this coupling length and this kind of space, right? So of course, we can theoretically make it, for example, the first pinch as a coupling length maybe like 7 millimeters, and the spacing is like the 5 millimeters, and the second one is the spacing is like 2 millimeters, something like that, right? And the problem is that if you add additional pinch, all the pinches need to adjusted, right? It's just an ideal case, right? And this one, proportional one, is more because to our mind, the easiest thing is that all the pinches are the same, right? And in that case, they will follow this kind of proportional model, right? So, and you may ask me that, why, if you think this one is practical, why do you still need this one, right? So this is because So if you are working, I just directly tell you some like tips. You do not need to read anymore. If you are working on boys and girls, if you are working on the machine learning or optimization, you use this proportional model. It works well and more practical. But if you work on the stochastic geometry, this performance analyze things, right? You need to use this model. Because if you're using this model for the performance analysis, the stochastic geometry will drive you crazy, right? If you have maybe 10 integrals and you cannot solve it one by one, right? So that's why I borrow a very famous person's the sentence. So because I'm more like modeling guy, so essentially all models are wrong, but some are useful, right? So we are trying to seek a trade-off between this kind of performance and the complexity. Because if you put the model too complicated, right? So you cannot get any insight. So if you put like the 10 integral there, right? So if you derive an equation like the 2 pages, who will read it, right? So this is the case. We need the clear and tidy design. And now let's move further, right? So now we are talking about this pinch. The basic principle is good, right? So and furtherly, we can do this kind of. So now we are just talk about pinch or not, right? So it's just a binary, right? But actually, we can make a bit further to make it as a continuous, like it's more like adjustable line, right? So we can pinch this. For example, we can put several like levels. We do the quantization. For example, we just to give you a random example. Maybe 0, 0 means like the 2 millimeters, and 1, 1 means 7 millimeters, and inside we still have 0, 1, 1, 0, right? So in that case, if you're talking about engineering people, you say that, okay, please do this, can adjust this space to maybe 2 millimeters or like 3 millimeters. So he or she will be crazy, right? But if you see that, okay, turn this 0, 0, turn this like 0, 1, so this should be fine, right? So this is we give a more like the adjustable power model, right? So this is the case. So now we are continue to talk about model, right? So now we have a lot of models, right? So this is called the amplitude constraint phase shift model, right? So we use this kind of multi-port, this kind of equivalent circuit model to do that, right? I just discussed with Professor Wen yesterday a bit for this kind of modeling. And he said that, okay, it's the model you currently use, perhaps it's not that feasible for or practical. Yeah, I fully agree. Yeah. So actually, but if you use it, if you do the real implementation, perhaps you need to rely on this kind of model. This is more practical. Yeah, to do the real implementation. But it's not friendly for the analyze. Right. So if I give this model and then show this kind of equations to our students, and then they open this my paper is can see that like 1 page is whole equations. They will just close it and see that. I will not play with you. Right? So this is the case, right? So this is I just try to make some trade-off. Right? But the good thing is that we in our recent work we put the different level of models like this kind of model and other proportional model, power model, different case models. So this is it's suitable for like the different so people who have different needs, right? So okay, so this is the modeling thing, right? I will skip this. So and also we have the if you use this model, we have some different needs. For example, when the phi is equal to 5 degrees, so this is more. This one is more sensitive to the space. How if you adjust, it's more sensitive. But if you use this one, yeah, so this is less sensitive, right? So this is also depends on your need. If you like to adjust this case. No, yeah, modeling finished, right? So this is my key contribution is finished, right? Now another key contribution of mine is like this kind of protocol design, right? Or active method design. So like the previous, if you follow my work on the start, I also very good at this kind of protocol design or activation method. Yeah. So this is like the user-centric activation. So what does it mean? So it means that, okay, I push, it's more like I have this kind of like the pinch, right? I put this in my pocket, right? And then I come over to the office, I see, oh, the signal is not that good. I put this pinch and pinch on this waveguide here, right? And then I will be sitting here and ask this kind of pinching antenna to serve me like this, right? And when I finish my work, I just get this kind of pinch, right? And I move to another place to have the meetings with my students, right? So I pinch this to another room, right? So this is the case, right? So of course you can argue me that okay, Yuanwei, this is very low, difficult to manage, a lot of security issue. I fully agree, right? As the beginning stage, it's fully agree, right? But in the end, I trust it will be some trade-off, like just something will be covered, something will be uncovered. I will just pinch something, yeah. Unless I saw this kind of power circuit track. Have you seen this before? Right. So previously, when I was in UK, one of my postdocs told me that, oh, this pinch antenna concept, it really look like this power socket track socket. But I never saw this before. In UK, I never saw this before. Until last time I traveled to mainland China, I saw this. Yes, they put this kind of, because there's very limited resource. They just the people are fight for this kind of socket. In that case, they put this thing, right? So this track is equivalent to our waveguide, and this socket is equivalent to our the pinch, right? So in that case, I say, okay, it is possible, right? So I like this idea, right? Okay, now let's talk about this kind of activation method, right? So we call this kind of activation method. This is like the first one we call this a discrete activation. So, and I'll give an example. It's more like the piano keyboard. You are playing the piano, right? So from the or you are the DJ, right? So you are playing some music, right? So this is someone like okay, say you are standing here and use these two pinches to serve you, right? And you move to this side, and these two pinches will serve you, right? And you move like the inside you activate this three. So this is some like the basic idea, right? So this is suitable for something like the things are moving fast, like the UAV communication, like the V2X communication. This can all done this thing, right? Because people are fast. You cannot do this. And the good thing is that it is fast response. This is electrical, right? And usually people like the electrical thing, right, rather than the mechanical, right? And the second thing is that the call is continuous activation. It's electrical curtain. This is an example. Use the electrical curtain, right? And then it's more like, okay, so you are there, just like electrical curtain, and then move there and from there. So this is more suitable for the indoor communications, right? Because it's slowly moved. But the good thing is that it is just need one pinch. This one we need multiple pinch, right? But actually it's okay, right? The pinch is very cheap, right? So in us, the RF chain is expensive, right? So, but the pinch is quite cheap, right? And also we go for this kind of like a semi-continuous activation, right? So we go for this semi-continuous. I really like this semi word. If you check my papers, a lot of this semi word, like a semi-ASIC, semi-normal, semi-thematic. This kind. It means that we do this kind of trade-off between 0 to 1. Yeah, this is the case, right? We got this kind of good trade-off. Right? Okay, now let's see the transmission architecture, right? I shared with you when I first when I first get in touch with the path, I feel very excited, clean and tidy. But I worked a bit. I feel a bit disappointment. I'm very worried because one waveguide can only transmit one single stream. It means that we cannot do MIMO. Right? So if some technique cannot be used for MIMO, it's not that promising, right? Because MIMO is a common accepted thing, common accepted technology. You can say OFDM is still like it still works well, right? So this is because in 6G nothing can replace it. So this is because it's well matched with MIMO, right? So we need to well match with MIMO. But how can we do that? Until my postdoc, so we found this kind of structure, right? So if one waveguide we cannot do MIMO, but multiple waveguide we can do MIMO, right? Right. So we can do the so-called this kind of waveguide multiplexing or waveguide division. Waveguide division means that each waveguide we transmit one single stream, right? But we connect all multiple data stream and fit it inside and then got this. And also I gave this very fancy name called pinching beamforming, right? So it's also acknowledged kind of a Docomo's like thing. But so and the multiplexing, waveguide multiplexing means that, okay, we have the transmit beamforming. This is what this can be the analog, can be digital, can be hybrid. This is what you did in the last maybe 20 years. When I was doing my PhD, I'm working on this kind of things, millimeter wave, massive MIMO, to this kind of thing, right? And the pinching beamforming is that so we can do the multiplexing with all multiple multiple data stream inside, and then fit to this pinching beamforming, right? So in that case, the pinching beamforming could be the replacement or add-on techniques. So for any existing MIMO networks, what does that mean? We can just rely on the pinching beamforming. We do not need the conventional transmit beamforming, right? But of course, we are not that accurate, but sometimes it's acceptable. This is called the replacement. This one is called the add-on, right? No matter what you have done for the conventional transmit beamforming, either digital, either analog or hybrid, we can do this additional pinching beamforming on top of the existing frame structure. So this is the case. So we propose this so-called tree-hybrid beamforming with 3 analog, digital, and the pinching beamforming, right? So this is fantastic, right? So because in that case, just like NOMA can be hot for so many years because it can be any add-on techniques for any existing infrastructure. No matter what kind of technique you are using, you can do NOMA on top of it, right? Until now, I feel happy, right? I say, okay, this is a promising direction. So I ask my students to work on it, right? So I mean, previously, just as last year, I just asked 4 or 5 my students or postdoc to work on it, right? But now I put a lot of more people work on it. Yeah, you know, as a supervisor, I sometimes feel very stressful and very so yeah, you know that sometimes you give a good topic so to the students, they will not really appreciate you, right? They say that, okay, this is your responsibility, right? But sometimes they give it the topic is not that hot. It's the he could not publish a paper. This is this is your responsibility. Why you give this the topic, right? So that's why when I push the new director, I feel also very nervous, right? But until now, I'm 100% confident that this topic would be very promising and very attractive. Yeah. So now let's another thing. Yes, I just discussed with Octavia and Professor Wen and Kashev a bit for this how to do this kind of multi-carrier things, right? So this is when I developed this class and I received a lot of emails to ask different questions, right? So how to do this kind of wideband transmission, how to do multi-carrier, how to do the channel estimation, how to do this blah blah different things, and hardware so impairment. Sometimes I see that, to be honest, I don't know. So, but I see that it would be the promising direction to work on because this is a very initial area. Right? So I will not go for detail, right? But the thing that for each mode we have the dominant mode. Right, for each the case, right, and also we got this kind of a single mode region. This is the case, and also we have this single mode region. This kind of upper limit, blah blah blah, right? And for the available bandwidth is that so upper limit is that ensure only one single mode to transmit in waveguide, right? And the lower limit is that it affects several factors such as material loss, tandem coupling, and feed structure limitations and cutoff frequencies of the mode, right? And this is also related to the things I mentioned to later. So for this kind of mode mode division path, something like that. Yeah. Okay, now let's talk another thing, the swan. Okay, this is proposed by one of my postdocs, Chong Yun. So this is also very clear and tidy, the message, right? So you know, when I got this and I received a lot of people emails asking me that how to do this uplink pass. Previously, I never saw this the uplink issue. They said that, okay, for example, this is the waveguide, right? We put multiple the pinch there, right? For the uplink, for example, you base it here, and those 3 pinch, these 3 pinches are received signal. But the signals received on this one will be possibly read out from this. How to solve this issue? Previously, I never thought about it until I received this. I started to consider this issue seriously. right? So that's why. So we propose this kind of uplink mode, right? So I think so, and so this is called the radiate issue from other pinch antennas. So for this one is more like, so we have a long waveguide, but we cut it in small pieces, right? And we ask each segment just to transmit, just to have one pinch on that. That's it. This is the case. And second one is like the in waveguide attenuation, right? So because I have introduced, they have some like the attenuation, right? So if you have too long, like 100 meters, the attenuation may be a problem, right? In that case, we need to cut it in 10 parts. Every part is just 10 meters, and we use some connector to connect that. Yeah. And then another thing is called the waveguide maintenance, right? Sometimes it's got some maintenance issue. For example, if we have 100 meters waveguide, the maintenance issue is also a problem. We need to take care of that. So this is the case. Right? So that's why we how to make the implementation path engineering feasible. To solve these three problems, we propose this segmented waveguide division. Enable the pinch antenna system, SWAN, right? So use this kind of SWAN, right? So we can see this is our base station, and this is like a colorful. Some like we make it like a colorful like the waveguide, right? And we make some multiple feeding point, right, to make it work, right? And this employ multiple short dielectric waveguide segment rearrangement to the end-to-end. And actually, each segment has its own feeding point to connect the base station through its wired one, right? So these three mentioned issue are solved, right? So for example, uplink signal, we by activate only one antenna per segment, right? And if we've got the attenuation, we just use this kind of segment level if we've got the attenuation. 10 meters, 20 meters, it's okay, right? And we've got the maintenance issue is like, so we use the segment level maintenance and the repair cost, right? So each one just take care of this 10 meters. It's okay, right? So in other words, SWAN is the engineering feasible design, right? We want this part, this fantastic part to be implemented in the future. We do some engineering level, engineering feasible, right? So we need some more clear and tidy design, right? So this is why it's good, right? But based on this, although this is very the SWAN the concept is very clear and tidy, very simple, very like basic, right? But based on this basic thing, we can do a lot of like the combinations, right? So for example, the operating protocols, we can do segment selection, right? We ask each option to switch between these things, yeah. And also we can do this kind of segment aggregation, right? We can ask all this kind of options to connect this kind of RF, right? Or we can do this kind of segment multiplexing, right? So we ask every option to connect one like the waveguide, right? Of course, they have there are like pros and cons. For example, they have the only option one, and for this segment selection, this performance is lowest, and but the implementation is very easy. It's like very low, and the second multiplexing is the highest performance, needs multiple options, and the performance is also good. So everything is a trade-off, right? And of course, we can also do this kind of tree hybrid beamforming as well from different angle, right? So we can do this switch-based architecture. Switch-based means that each waveguide we have this kind of switch to do this switching, right? And also this switch-based architecture could be fully connected or sub-connected, right? And also we can do this kind of phase shifter-based architecture. This phase shifter based architecture and could be the fully connected or sub-connected, right? So to here is already very complicated, but they are originated from the very simple, clear and tidy SWAN design, right? So this is the beauty of the path. Okay, yeah. And now let's share some more exciting thing, right? So this is the last. Go ahead. Yeah, I think that is the very good question. Right. So I think, to be honest, so I never thought about this issue before because this is, yeah. But now we just use this 100 meters just like the equally like the divided in 10 parts, right? But I trust, as you mentioned, cache app, so we can do this kind of maybe non-uniform like the card, and we just and each like just use the connector between this, right? So I trust it should be suitable for you like the deployment for some rooms, maybe less, some rooms should be long, something like this. Right? So this should be a good idea. Someone put more pinches, some maybe uplink or just one pinch. So this is depends on the requirements. Yeah. Now let's share the one very like the recent like the results. Actually, this one is just I worked very heavy in last 2 months. Yeah. So this is called the CPAS. Yeah. So actually, I just archived this paper like yesterday, right? So and I didn't even include this in our global comm tutorial. So this is the first time I presented it here. You can see, and I was still a bit nervous. I was sitting there and prepare some like some slides and see some notes, right? And Octavia also encouraged me, Yuanwei, do not be like scared, do not be nervous, right? So this is just like the new content. Yeah. Yeah. So, but this is also very like you can see I still feel very nervous, right? So no, I'm just kidding. Yeah. So this is the case is that okay. So why we need this the CPAS, right? You can see previously we said that from the original thing one waveguide we can only transmit one single stream, which means that with one waveguide we cannot do MIMO. I feel very disappointed, right? And then I feel that okay, with multiple waveguide we can do the MIMO, right? So, but for me, I'm always something like greedy, right? I mean, greedy on research, right? No, not on other things, right? So I just want to see that, how is that possible? We just use one waveguide to do this MIMO, right? So this is the purpose we propose this CPAS. Now let's see. So single waveguide cannot do the MIMO, right? So this is because okay, we have this is a conventional and feed path like this, right? So we put these two RF chain here, and there's two signals, but we cannot do MIMO. This is because we can understand from two perspectives. The first perspective is from this channel itself, because they share the same channel. They're like the linear combination, right? So the only difference is just the phase. That's why we cannot distinguish the two signals, right? Or we can, from another perspective, call this kind of from mathematics. This is the effective signal. X1 like multiply equal like exponents blah blah something like this. So this is because this cannot distinguish because X1 and X2 because they are linear superposition from mathematical perspective. But anyway, we cannot do MIMO with single waveguide if we do this from the conventional and feed. How about we change the angle? We fix this in the middle. Yeah. But this is just we need RF, two RF. This is just an RF chain. Anyway, we need 2 or 3 so here. So we can. So this one is that we put it here and put a power splitter here, and the signals can be read out from 2 directions. Right. And the 2 pins here, there was like the for example, 2 users here. And in that case, we will have some space diversity. Sorry, it's a space multiplexing. There's some space difference. So this is, in that case, we can do MIMO. We got the DOM. Right? So, in other words, you know how I like the motivate. This is because of the star. This is like the conventional race. This is like the star. Right? So it's more like 2 direction. Star is more like the reflection transmission. This is like the backward forward, right? We got this still need to follow this kind of energy like the conservation law, right? So and also we got this power splitter and also this kind of thing. So one extending and also this can be extended to endpoints, right? So when extended to endpoint CPAS, the outcome is like the weighted sum of the output, right? So this is you can see we just submitted this letter. It's just put this on cap today, so you can just check. This is quite interesting. And also we can do this performance analysis. We need to theoretically demonstrate. So this is just my imagination. I always think, okay, possibly it's 2. The DOF is double. It's all can be m like times. But if you take we do this DOF analysis, we calculate the power scan low, right? So this is my advantage, right? So when I first do my PhD in the 2013, so actually I was working on this kind of performance analysis, the kind of geometry, this DOF analyze, power scan low. This is my like initial start of my research, right? Something like that. Okay, so we can. So this is our centered feed like path. Okay, this is 2, and the conventional one is 1, right? And also we got this kind of multiplexing, right? So, and we can see new results. We can see this is the conventional one, slope is 1, and this is our C path, slope is 2. This actually is a DOF, higher than slope, right? And this is the so-called the center. This is again, right, compared to the conventional path. That's why we prefer to put it in the center, right? Yeah, another thing now. This is another work we are working on, right? So this is hopefully we can finish within this month. That's actually, so this is like the practical optical protocol. This is like a star, right? So for example, this first means that, okay, we put the 2 RF chain here, and then we put 2 power splitter, and the signals can be do this like the backward or forward, right, to do some different combination. And this one is called the dual direction switching. Direction switching means that, okay, we put the switch here, and we just put the switch left and to ask the signal there, to left, and the switch right to ask signal to switch right. Yeah. So this is direction switching, and this one is called time switching. Time switching is very easy to understand. It's just like the blind there, right? We turn it on to make it to do the right, and turn it off on the left. So this is another thing we are working on. Yeah. And also we have this, of course, different protocols is have like different like the advantage, pros and cons. Right? So this is the case is that, okay, so we got this kind of different protocols. We got these advantages and disadvantages. So we go for the power splitting. So of course it has the highest flexibility, but we need a large number of design variables to be optimized, because every splitter you need to optimize. This is a continuous, right? The second one is called the direction switching. It means it is easy to implement, right? But it's reduced again compared to with power splitting. TS is independent. So we have the independent like the F and B mode design, forward and backward, right? But this is a high hardware implementation complexity, right? So this is the case, right? So this is of course every protocol has its own protocol. Yeah, it's just like you will never have your Mr. Perfect, but you just need your Mr. like the right something, right? So and then we can do this kind of pass this kind of like the signals to the 6G and beyond, right? So we see what kind of application scenarios we can do, right? So this is like the so we can first we start with this kind of indoor communication, right? So indoor communication and actually a lot of people are talking about the path is for this kind of starting with indoor communication, because they are focused on this line of sight, right? So we do this line of sight creation, right? So especially for the high frequency, right? So I just give you an example for the 6G base station, like the millimeter wave and terahertz. So previously, if you ask a 6G base station, outdoor base station to serve the indoor users, it's not possible, right? So because it's not possible, because for this they are very sensitive to the blockage, right? So for example, okay, if you do this kind of now. It's more like, okay, we put this kind of waveguide inside. It's more like the pipe, right? And to inside and to overcome this kind of highly like propagation, this issue, and then use this kind of like the pinch just on your top to serve you, right? Like the millimeter wave or terahertz. So in that case, it's very, very friendly to this kind of like the high frequency. Right? Another thing is for normal. Yeah, so it's one of my major original like the research direction. Right. Previously, if you have 3 users, right? So you can only do the SS in this first user, the nearest user, because it has the strongest channel gain, right? So whether it's like the IoT user as like a video user, so you have to do this SS here. But sometimes it's just like IoT user. I do not need so much bandwidth. Why do you give me so much bandwidth, right? So, but now, so we can do the SS here by adding more pinches here, generating the array gain. Array gain, so this has to be the better channel, right? So in that case, we can do the SS here, right? So which means that we can, with the path, we can make normal more flexible. Another beauty of this path is for this NICE or iSiC, right? I would like to say that, okay, so iSiC, I think Zhiguo also mentioned yesterday, so iSiC is very like the fantastic, like the promising, like the direction. This is because now wireless people, we want some applications, right, to make money, right? So I mean the companies, right? So if you see that, okay, I have a mobile phone, and and I can make you very fast to get some like the online gaming, VR gaming, this kind of thing. You may say that, oh, maybe I'm not really like care about that. Low latency, sometimes I do not care, right? Maybe you do not care, right? But you see that, okay, with your mobile phone, right, you can do some sensing activity, like application. You can sense who is behind this wall. You will say, oh, this is good, right? I like it. I like this kind of idea. I want this is because sensing gives us wireless people a lot of imaginations, right? A lot of hope, a lot of like good things to make money, to get something, right? So that's why everyone is taking care of this sensing, right? And the near field sensing, nice. This is also I am heavily pushed idea, as I mentioned, right? So this near field sensing can do what? This can track the trajectory of the UAV or the cars or moving targets. Previously, we can only use this kind of camera to do that, but the wire signal itself is very powerful, right? So because previously all the assumptions are based on the far field, based on this kind of like that's a planar wave assumption, but in reality, no electromagnetic wave is planar. All electromagnetic waves are the spherical wave, right? So previously we simplified this a bit, but this doesn't mean that the previous thing is wrong, because now we're just because previously we do not have a lot of antennas, we do not have very high frequencies, we do not have very large apertures, right? So now we have the larger and larger antennas, like previously we have MIMO, then massive MIMO, then extremely massive MIMO, then some kappa, right? And then we have higher and higher frequencies. Previously, we do work on sub-6G. Now we move to the millimeter wave. Now we move to the terahertz, right? Now we have the, so this is the case, right? So that's why now NICE is very near field become popular, right? But how to achieve near field? As I mentioned, we cannot put the whole world as near field and as aperture, right? But we can put the waveguide there to achieve the near field. This is relatively easy, and also it is very, very like friendly for the sensing, right? So this is the selling point. To be honest, from my perspective, I trust the path can do more for sensing rather than communication. I mean, yeah. So this is also I discussed with Octavia a bit. So this is I think this is the case. Okay, and also we can do this kind of this is another thing we can do for the low altitude. You know, the low altitude economy is very popular in the mainland China. So when I moved there and moved to Hong Kong, and a lot of people come over to me say that Yuanwei, let's work on the low altitude economy, right? And I asked them, so excuse me, so what is low altitude economy? I have never heard about this word, right? And they told me that it means that you have UAV to do this kind of trajectory design, do this kind of, for example, this thing. I say, oh, this is what I did in this UAV communication when I was in the PhD, right? It's already 10 years ago, right? But but it's because of funding, right? So actually, currently, more than 80% of my summit fundings are related to this kind of low-energy economy, right? So, and then they ask me, okay, so this low-energy, so now as I worked a bit, I realized what's the difference between the UAV conventional UAV communication and the low-energy economy, right? So two things. The first thing is about this kind of interference mitigation. What does that mean? Previously, all the because we are working all the base stations are facing down, right? So this is to serve because to serve our mobile users. But now if you have some aerial users, they need to facing up, right? To face up, right? And face up means that you generate a lot of interference. If you are facing down, we just need to take care of this overlapped the region. But if they are face to face, right, so this is a problem, right? And another thing that the UAV is like flying up and down, right? So you cannot make this you attend like this, right? So this is like the mechanical, like the facing down, facing up. This is not possible, right? So that's why we can use this kind of pinch to do this. Right. For example, the UAV is for working here, and then we activate it here. And if you work and you are moving forward, like up, you can do this. Discrete activation is just like playing the piano. You are the DJ to do something. This is the case. Right. And the second thing, the case is for this kind of sensing, low energy economy. Because previously we do not focus on sensing, but now we think that we need to do this kind of sensing. We need to know where the UAV is, right? So where the HAPS is, and what is this kind of thing, right? And then it should be some combination. It's like iSAC, radar, and it should be multimode sensing. Because now I'm in charge of a very large project of this RAE, right? A low energy economy. And a lot of people approach me. They're selling their own idea. So the iSAC people see that, oh, the iSAC is fantastic, blah, blah, blah. And radar people see that, okay, can use the radar to do this fantastic sensing. And the camera people could approach me and say, yeah, we can do this camera to do this kind of fantastic sensing. Of course, they are selling their own idea. But now, after long time, so we developed, so for myself, I developed this kind of multi-modality like sensing. So what does that mean? It means that we use this kind of iSAC base station to do this first step sensing. It's more like there's a blurry, we can see that. Right? Just like we open the net, we say, oh, there's people there. Right? And then we use this kind of radar to go this direction, to sense, okay, there's something. But the radar, the problem is that sometimes it got a lot of like alert. Right, so it's not that accurate, yeah. And say, okay, there is something there, but for the radar, it cannot distinguish this it's a bird or UAV or plastic or something, right? And then we ask this kind of camera to go this direction, right? So then we can see that is. So this is what the approach I developed. So for this one, but this is, this is related to this path. This is the difference to the. So in our world, we can use the path to do this low energy economy. So in a very efficient way to do the sensing. Yeah. 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 In that case, we need to we have a lot of buildings, right? We can do this kind of cooperative sensing. Yeah, so we do actually this one, and then we can just do this cooperative side. Okay, so yeah, do we need to take a break or something? Or we can go continue? Yeah, it's fine. No, we can go. Yeah, so, of course I can always talk. Yeah, so 2 hours, 3 hours is fine. Yes, I'm a good talker, right? So. Yeah, so but just I'm a bit worried they want to go to some washroom. But if you want to go, so free for to go, and otherwise you can stay here. Yeah. Okay, so now we finished the first part, the path basis. Now we move the second part. The part means case studies, right? So start with this kind of performance analysis. This is one of my So now this is the first work of ours for the performance analysis, right? So we try to analyze, and actually, every this kind of new work, what I think I need to describe is that what is like, what will be different, right? So what will be different means that, okay, so here for path, the two difference. The first thing is the near field model. The model is 100% near field. If you use a far field model, sorry, so you need to, no matter how long your paper is already finished, you need to redo that, right? The second thing is this pinching beamforming, because it is more complicated than the star. Because for the star, so every element, so we just adjust the phase, and the phase and amplitude, they are decoupled. But for this pinch, the phase and amplitude, they are coupled together, right? So this is the problem, right? So you move this pinch, you adjust both phase and amplitude. Amplitude means the path loss, right? So now we try to answer these two questions. The first one is that for the fixed inter-antenna spacing, does the region increase like the monotonically with the number of the antennas? The second is that for the fixed antenna number, does the region increase as the inter-antenna spacing decreases? Or in other words, we are trying to answer the question, how many antennas do we need? Okay, so this is the two questions that happened in the conventional massive MIMO. For the conventional massive MIMO, the answer is yes, right? So yes, sometimes I expect some like abnormal like answers, right? Because if you consistent with the conventional massive MIMO, I lose my interest, right? That is also, I talked a lot with my postdoc students, right? So you need to propose something also make me also excited, right? Inspire me. So I'm very boring every day, right? So this is like, I want something can initiate like a research interest, right? So this one is the work. The answer is no. It's quite surprising. Yes. So this is it's because when they run this figure, I feel very like I cannot understand that. This is the figure, right? So we can see this figure. So there is an optimal like the pinch antennas, right? So which means that the two answers are no, which is inconsistent with the conventional MIMO, massive MIMO. So which means that optimizing the location and numbers of pinch antenna is important. We go to optimal point, we go to trade-off. That's why we need to optimize, right? So why is that? Yeah, so because I'm not go for the technical details, I just give you some like the high level like the explanation. It's because of the aperture loss, because this is near field. So what is aperture loss? I give you an example. You go to the cinema, right? So you sit in the first row, right? You cannot, first row is not good, right? Because you cannot see the entire like the screen. You need to watch the film like this, right? And assume that you are the scatter there. You are scattered here, right? So you cannot, you just reflect this small region, visible region. So this is why we will get this kind of things, right? So this is quite interesting, right? And we can go this kind of, so we have an optimal number of and the locations for this. So this is a very nice work. I love it a lot. Yeah. And then we go for this kind of swan for metanalyzer, right? So we do this. I just give you some like this swan. We can do this kind of segment selection. We can get some segment aggregation, segment multiplexing. Yeah. So what I want to show is here. Usually I do not put equations on this kind of metanalyzer, but here I put this very simple equation here because I just want you to realize it is really not that difficult. It's very clear and tidy. Yeah. So, and also we got this uplink swan, downlink swan. I got some like the insights. This means that the swan can reduce both the large scale path loss and the in-waveguide propagation, and which can significantly enhance the SR compared to the conventional path, right? Among the three protocols, and also says SM and for example, like everyone has its pros and cons. But sometimes best performance, sometimes best and like the complexity, blah blah. It's everything is trade-off. Yeah. This is a figure I demonstrate Right, so this is a scenario. I demonstrate that. Okay, so when you go to your office, you will press press a button to ask the attendant to pinch, and when you leave, and you release the button, something like that. Right. So yeah, I'll skip this kind of details. We got this kind of perfect antenna again. This kind of better fairness for this uplink. The second important thing, beamforming. So beamforming is very hot and very internal topics for each new case, right? Because if you check the best paper award of the transaction, like TWC, TCOM, common letter, blah blah, this kind of thing, the most awardees they are working. I mean, the awarded topics they are beamforming, right? Because this is it's the first initial stage, and also it is the practical, something like that. So now let's see this kind of pinching beamforming. This pinching beamforming is more like, okay, compared with the conventional beamforming. So what will be the different conventional MIMO? Because for MIMO people, star people, we have done this kind of thing for so many years. So what is new? What will be different? Now I directly tell you. The first one is in waveguide propagation. The second thing is that there's a pinching beamforming. Right? So previously we do not have this pinching beamforming. And the pinching beamforming is that they are highly coupled objective functions, because the phase and the path loss, they are highly coupled. They are much more complicated than the star rays. Right? And also this results, we have a large number of local optimum. Right? So this is a problem. Right? So now we use this, but for me, you use this kind of penalty-based algorithm. Right? So penalty-based algorithm to solve this kind of decouple problem, to decouple this to optimization variables, and actually which enables just like one-dimensional search to replace the inefficient this kind of gradient or coordinated distance things. Right? The second thing is like zero forcing based. Right? So we have this kind of zero forcing beamformer, blah blah blah, to solve this this one. And then another surprise is for these two figures, right? So actually this work is developed by Zhao Lin, and when he showed me this figure, I could not believe that. You can see this is SNR, this is transmit power. Because we are using the energy efficiency, means that the lower the better, right? So and when we select the benchmark, we see that, okay, what is our benchmark? I usually will use MIMO, conventional MIMO or massive MIMO to do the benchmark, right? So MIMO is here, and the massive MIMO is here, and the pinching antenna is here. I could not believe, how can you beat massive MIMO so much? It's not possible, right? And then I asked Zhao Lin, so is your simulation, these parameters and the environment? And he told me it's more something like that. That is the base station, massive MIMO base station, right? And so massive MIMO is like from base station to serve me wirelessly, right? And the pinching antenna is that, so from that base station and get a pin waveguide to here, and then put the pinch here to serve me. Of course, you can beat massive MIMO a lot, right? Because you have a quite shorter distance, 10 meters, 1 meter. Of course, you win. You may argue that, oh, you are not provide the fair comparison, so it's not fair. So how can you do this? The 10 meters compare 1 meter. I fully agree, but this is the purpose we want to use the path. This is the reality, right? So that's why we just want to do. We are doing this kind of the so-called loss creation. Right. Okay, so now let's move further, right? To do this kind of I got a lot of like this kind of the second thing is called the LLM, large language model, right? I got a lot of like fancy students. They are much fancier than me, right? So usually they want to do something like trace the large language model, MOE, this kind of things, right? So they want to use this large language model to solve this problem. I say, yeah, perhaps yes, yeah. So, but I actually am like I like AI. I do love AI. It's perfect, right? So, but I'm not really a fan of this AI for everything. right? So you need to find this trade-off. You need to find this kind of trigger point, right? So, and then for in this work, we try to answer a question, optimization based or learning based, right? Because this is, I still remember that sometimes I give a talk in some places, and then one student and I were talking about this kind of optimal solution, blah blah something this, and one student asked me, and asked me, "Hi Yuanwei, can this problem solved by the machine learning?" I say, yeah, perhaps, but why do you ask? Because then he answered that because I do not want to learn the mathematics. Yeah, so something is like that, but this is the wrong like that. But if you want to do deeper in the machine learning, you need to do this kind of mathematics. You need to learn mathematics a lot, right? So that's why the first, if a student, my student come over to me, say that I want to use the large language model to solve this problem, and the first question I ask him or her is that, can this problem be solved by the conventional optimization approach? If yes, why do you want to use the machine learning? You need to first convince me before you do this, right? So this is the case. And then we go for this kind of thing. That go for this like blah blah. So first we still use the penalty based. This is as a benchmark to say, okay, this is like conventional. We got the KKT solution, stationary point, this kind of thing, because we have numerical sample optimal solution, something like that. So then we use the LLM. We based on the like the transformer, right? So like for example, we got this kind of when we see that one KKT means the large language model, right? So we try to get some like the chemical like combination, not a physical combination. We want to make generate some 1 + 1 is greater than 2 effect, right? And then we go for this king, and then we do this kind of leverage the power LLM, and so we do this from the CSI to beamforming mapping, sequence to sequence generation, blah blah, self attention. So CSI beamforming dependence across like attention. This is something like this. Yeah. And then we do this kind of pinching beamforming, and we go this kind of optimize, and we answer the question optimization based and learning based. We demonstrate our KKD has a very good performance and with acceptable like complexity. Yeah. Yeah. Another. Yeah. So like the fancy like the gentleman. Yeah. So yeah. He made something like this kind of GNN method, right? Like but this is got some also, but all this kind of my fancy students, they do some like the design, right? Because this one this you cannot directly use download the code from the GitHub and run it and do this thing. You cannot do that. It's not that directly, because you need to redesign these GNN networks, right? So either for this kind of pinching beamforming and transmit beamforming, you need, because pinching beamforming is new. Previously, no one designed this GNN networks for the pinching beamforming. You need to do this manually, right? And also, this is GNN is more like the learning beamforming. You also need to do this, right? So this is, and when we do the combination, because they are highly coupled, you need to take care of this properly. So this is not easy. It's not like a this is kind of like good contributions from my point. Yeah. So there's some similar results. So it demonstrates this some case. Yeah. Yeah. This one, I pretty like this work. Beamforming design. You can see I did a lot of beamforming, right? So like from the modeling to the LLM, like the GNN and also the optimal. Yeah. Actually, this one I like it because, as I mentioned, these two parameters are highly coupled. So it's very difficult to get the optimal solution, right? But actually, I'm like the optimal guy, right? So if you check all my work, so always I seek for the optimal solution because I hate suboptimal, right? So why? Because 10% of the optimal solution is suboptimal. 99% of the optimal is still the suboptimal. We do need the benchmark. Right? So then we use this kind of big branch and bound to get the global optimal beamforming. You may argue that, oh, you have a branch and bounds, it's very silly. It's just like you do this kind of exhaustive search, blah, blah, do this kind of thing. I fully agree, right? But it requires a lot, but it can provide us the benchmark, right? Because, okay, if we can get, okay, global optimal one to show that, okay, this is your benchmark, right? It's just like a channel. He provides a bound. Everybody needs to compare with him, right? And now we got the near optimal solution with low complexity, right? And then we can demonstrate this kind of suboptimal can achieve the almost the optimal, near optimal solution with low complexity. You are doing a good job, right? So this is my point. That's why I pretty like this work. Yeah. Of course, it's not easy. Branch and bound. If you trying to do the coding, you can try. It's a lot of work. It's like it's equivalent to do the with 3 or 4 like the matching papers. Yeah, that's why. So yeah, this is good. Okay, now we move to this kind of so-called multiple access, right? So I'm a multiple access guy, right? So and okay, so multiple access, and we propose this so-called the waveguide division multiple access. So what does that mean? It means that, as I mentioned, that so we can do 2 things, right? So waveguide division or waveguide multiplexing. Waveguide division means that each waveguide we transmit the same like the stream, right? And this colorful thing, it means that they are from different. So this is time domain, it's frequency domain. You can regard it as waveguide domain, right? So why we need this? So with this thing, we can do this with the pinching beamforming. So we can like make the desired signal enhancement and the interference mitigation to achieve the near orthogonality in the free space. What does that mean? For example, the waveguide is there, and there's a pinch to serve me, right? And another waveguide is at that corner, and there's a pinch to serve, and that's a gentleman, yeah. And so this is so this is good, right? So and then this pinch is serving me. So if you generate very less interference to the gentleman, and the same, the pinch there generates very less like interference to me, right? So although we are in the same space, but we can achieve the near orthogonality. So this is much easier, right? And also, yeah, we will skip we do this pinching beamforming, use a continuous activation, discrete FA. I will skip this kind of this design. So I just show you result. Okay, this is user 1, this is user 2. We can see in the same space we got the near optimal. Sorry, near is we got the same space. We got the near orthogonality. So this is good. And then some similar results for this multiple site design. Yeah. So another thing, beam training and the channel estimation. So beam training and the channel estimation are the internal topics for each generation or each new topics. For example, every topics come out. For example, MIMO, massive MIMO, millimeter wave, star rays, mobile tunnel, so blah blah something. Everything you need to do this channel estimation or beam training because you need to know the H. Or you need to know the DOA or DOI, right? So this is the case, right? So similar thing happened for the path, but path is more challenging compared to star or star rays, because if for the star, this is the star, it's just 16 elements. You just need to estimate the 16 positions. That's it, right? But for the waveguide, for the pinch, right? So every position could be the pinching position. It's continuously. Right. So also they share the same stream. You need to use the low rank matrix to estimate the high rank matrix. It's not easy, right? So how can I do that, right? So for myself, I start with some very easy to follow method from the beam training. Beam training is much easier, right? So it's much like we just need to know the DOA, blah blah, this kind of thing, right? So we do this kind of. We make 3 methods. First one is called this kind of pinching. So we have the pinch, and we have 1 waveguide and 1 pinch, right? So 1 waveguide, 1 user, right? So this is single waveguide, single user. This is first, this simplest one, right? We do this kind of 3-stage beam training, blah blah blah, stage 1, stage 2, 3, right? And the second discussion is about this kind of single waveguide multi-user. In that case, we have to use norma to solve it. Right, so 1 waveguide, multiple user. We have to use norma to solve it. Right. So the second one, the third one would be the multiple waveguide, multiple user, right? So this is like a more general case, right? And in that case, we need to use, this is the way we need to do this kind of increase the dimension of the codebook design. And then we go to this increase the three SBT message, blah, blah, stage 1, stage 2, stage 3. Yeah. So this is the case from the easiest thing to the next, to the more complicated thing, right? And then we compare all this performance and all the training overhead for this thing, right? And we demonstrate that we got the reduced training overhead when maintaining the reasonable rate, right? And got that can better flexibility and improve the system performance. Right? Then channel estimation, right? As I mentioned, the channel estimation is the internal topics, and people may argue that, oh yeah, why do you still need the channel estimation, right? So you are focusing on line side. Yes and no, right? So of course, so we aim to generate this kind of line side, right? But if we have waveguide here, do this pinching, of course we can serve somebody outside of this door. No matter you want or not, we have this thing, right? So non-line side, right? So if you want to utilize this non-line side, you need to do this kind of channel estimation. You need to know the channel, right? So how to do this, right? So for example, this is a scatter, blah, blah, blah. Of course, yeah, I also discussed with Professor Wim yesterday to say that, okay, of course, we focus on lamp side, but no matter you want or not, you still have some scatter, just like a millimeter wave, right? So we still have some scatter, right? Maybe sparse, maybe blah, blah, right? So in that case, we need to know the channel. We need to know the channel, right? And actually, and the first challenge for channel estimation of path is that we have the arbitrary position and the arbitrary number of PAs. We don't know. We don't know where to pinch. We don't know how many pinches are there. It's not like star. When the star is there, already we know that. So this is the first challenge, right? And also the estimation like channel, cascading channel. So it's like this is not enough for the PA optimization. Slow rank, right? And we got the individual channel. This is like an underdetermined recovery problem. This is another thing. And also we got the challenges, for example, the deterministic in the waveguide, like analog combining, right? So because we have a fixed PA position, resulting in, for example, limited measurement diversity, inadequate like matrix rank, and inefficient multi-user orthogonality, orthogonal like penalty utilization. This is all the challenges, right? So if you use this kind of antenna switching based blah blah this kind of thing, right? So we will go to this thing. For example, the limited estimation accuracy, because we lost the spatial diversity, right? So and also we got the unnecessary hardware overhead and the extended measurement time, and also potential space loss. It's a lot of problem to be solved. How to do that, right? Then another of my fancy collaborator, they use this kind of MOE. Perhaps you know this because of DeepSeek. They use this kind of mixture of experts. Yeah, but this paper is good. This paper is good, and it's accepted and solve this problem, right? So this is this is good, but it's not fantastic. Yeah. Why? Because this is MOE. You can use MOE to solve this path problem. You can also use MOE to solve this kind of like the stars, the massive MIMO, whatever, right? So this is like the general version, right? Just like you go to buy a bag, right? Why the women's they lack this kind of limited version bag, yeah? Because it means that it's just for you, right? But if you see that okay, so everyone can buy this every way, so it's not that. And this is something. So that's why we want some like specific design for this path. Until now, I do not have an idea to do this. If some of our boys and girls, our talented young people, you can do this. So please help. Yes, for myself, I didn't get a very proper version to get some channel estimation specific to this path. Yeah, because it's not an easy problem, as I mentioned. Okay, so this is like the outline. Yeah, the last one I want to talk about is like application. Yes, applications for path, right? Yeah, no worries. I will finish in 10 minutes. I'll leave some more questions. Yeah. Then let's say, so I'm very talkative, right? So this is a problem. I will finish in 10 minutes, right? Yeah. The first thing is like the wireless sensing, right? So wireless sensing means that, okay, so this is a path for wireless sensing. So the thing we did is that we use one pinch antenna to do the like the transmission, and the one RCX cable as a receiving, right? So this is our design, right? So the reason is that so when you do this kind of pinching to a target, we want this to be reflected to as many as possible because the many like the more echoes to make it more accurate, right? So and also we can do a lot of like slots here to do this, right? So this is the case. And yeah, we do this kind of this is the iSAC, right? We do this wireless sensing to do for this and pinching beamforming, transmit beamforming, blah blah blah. And then we got this kind of path for sensing, and we see that the path near like very like lower sensing error bound. Yeah. And another design is that we use one pinching antenna to do the transmission, and another pinching antenna to do the receiving, to do the receiver, right? And so when I developed these two ideas, and I also received a lot of emails, and people ask me that, so Yuanwei, can we use one single pinch like the waveguide to do the transmitting and the receiving at the same time simultaneously? I said, maybe, but I do not encourage to do that. And he replied me, why? So I want to do some challenging problem, right? But actually, you can imagine it will be very complicated from my mind, right? So you need to control this kind of backward, forward, this kind of propagation. It's very complicated, right? Right. Our life is tough, right? We need to make it easier, right? So this is I never encourage you to do this transmitting and receiving. I mean, iSAC with the same waveguide, separated it. Yeah. So in that case, you make it much clear and tidy. And then we go for this kind of like the rate region, right? So we can do this kind of communication-centric iSAC. Communication-centric means that our main aim is for the communication, right? The sensing is our byproduct. And also we can do this sensing-centric, means that we aim for sensing, but communication is like a byproduct. Right? And the last one, it could be some pretty optimal, it's like our rate region. We want to do this. Yeah, so we demonstrate this is our. So this is a sensing rate, communication rate. This is our trade-off, right? So this sensing, you may ask me some what is sensing rate. I can explain later. So this is based on our another push direction called the iSAC from the like the mutual information perspective. Yeah. So this is also interesting. Yeah. And last, I will go very quickly with this kind of physical security thing, right? Because a lot of people are working on this, right? So here I think that we got some design. This is interesting. So we can see we all know what is artificial noise, right? So the first thing that this is more like the waveguide deviation, right? So when you use one waveguide to transmit the signal and another one to transmit the artificial noise. The second one is that we mix the transmit signal and artificial noise together with the spatial multiplexing, and then with the basic and beamforming, and then transmit it together like the waveguide multiplexing. This is okay. And then we got some results. Yeah. And also some physical security work. I will, for example, single wave bob, single wave, and multiple bob, multiple wave, and other things. Yeah. And here, yeah, this I want to talk a bit. Yeah. So below here, this is more like we want to hiding the motivation is hiding the legitimate transmission from the watchful warden. Or we call it the forbidden zone, or like the protected zone, right? So for example, it means that so in some area we cannot put the eavesdropper there, right? Just like, okay, if somebody is eavesdropper outside, we cannot see them. But if somebody is in this room, I can see him, right? So he or she cannot stay here. So this is the case. Yeah. And then we go for, now we move to the research challenge and the opportunities. Yeah, as I mentioned, we just initiated this direction since last year. This is very up-to-date research, right? We still have a lot of problem to be solved, right? So for example, the hardware implementation, how to do this, right? How to do the demo, right? How to do a proper demo, and what is the channel measurement? So what is really the channel for this? Currently, there's no idea. And also the applicability receiving design. Now we are more or less solved it by the segment part, by the more or less we solve this. And also beamforming with some practical or constraint or complicated constraints, right? More practical. And also we can do the flexible pinching power allocation, right? So now what I in for example, now the multiple now for example, one waveguide, multiple pinch, how to do the pinching allocation. We can do that. Not just a pinch or not. We can do the continuous, how to allocate the power, just like the just like a normal, right? The basic thing is that from the single antenna, multiple user, right? And then we move to MIMO normal, right? Another multiple set design, right? So we how to do a clean and tidy design, right? With normal or with no normal waveguide division, multiple sets is also fine, right? So which is the best performance analysis, the multiple sets, right? Also, this is a tree hybrid beamforming. So how to make the efficient combination between the analog, digital, and the pinching beamforming, right? And also this spatial analyze, right? For example, if we want to deploy some like pinch in our campus, right? How many pinches? How many paths do we need? How many waveguide do we need? In what's the like density between the base station users and the pinch? So this is the case, right? And also paths for this kind of non-terrestrial and satellite communications, right? So with long distance, how can we solve this? Perhaps for sensing or something, right? And also the channel estimation. This is a very challenging problem, right? And also this is like the machine learning or edge intelligence, right? So how to use the machine learning or intelligence to do that, our large language model, blah, blah. And how to do this kind of ASIC, right? Path enabled ASIC, how to use path to sensing, and localization, near field sensing or localization, and how to do this kind of for high frequency one to enable this is more case, and how to do this sparse or distributed antenna design for paths either for sensing or communication. Okay, so yeah, this is the slides. So if you can, yeah, so you can just scan the QR code and download the slides. Yeah, previously usually I reply the email very quickly, right? So and if people ask me for the slides, I will send them back very quickly. But now because I'm like more like getting older, right? So I'm very a bit like not that efficient. That's why I just be lazy and put the slides here. Yeah, and another promotion. So with Kaibin, so we established the 6G at Hong Kong U. So we're trying to like do this technical driven and like academic industry collaboration, right? So we are open to every like region. So like because now you can like Hong Kong is more like the hub, right? So we can connect in the world. Right? And also we do the research projects, customer like graduate program, executive like training certification, and also visiting scholar and expert lectures, right? And also they can we go this by this kind of leverage research. We got some sponsor research like gifts to projects, contract projects, and named laboratory, right? So we got some name with some industry with a named laboratory, and this is our 6 Hong Kong U. So we got some like space, yeah. So if you want to know more, so you can just scan this QR code and get some more information. Okay, so this is the end of my talk. If you have any questions, I'm happy to address. Thank you.
Yeah, I have a question, Professor.
So please wait. First, let's finish a question from our audience. Then we will go to online audience. Okay.
Oh, yeah. I finished my question. I just want to ask is it possible to insert the analog phaser into the pinch? Yeah.
Yeah. So okay. So yeah, just yes. The simple answer is yes. Yes. But for it, I assume that you want to add some additional phase shifter on this kind of like the waveguide or something, right? Yeah. So theoretically speaking, its answer is yes. But how do that? I don't know. So you need to, because you need to, I assume that you need to make some special feeding point, right? So, and also with some phase shifters, right, on that. But I trust Professor Ren, you know more than me. Right? But for me, this kind of modeling, theoretical from should be okay. Yes, I think totally fine. Yeah.
That was a really wonderful talk. So basically, what I understood from yesterday from Chigo's talk and yours is that so this pinching antenna. So a lot of it is based on the actually mechanically modifying the properties of actual electromagnetic hardware, like through Maxwell equation and all those things, right? So we no longer require those active energy elements like RF chains and all those that we have in conventional RF antennas. Am I making any sense?
Sorry, can you repeat the last sentence?
So in conventional antennas, the RF chains that we have,
Yeah.
so they are no longer included here, right? When we talk about pinching.
They are still there. So can we go back to my slides? They are still there.
Oh,
They're still there. So and another thing is that so you go last. Yeah. So we can go see, and the R. So this is the thing. So one RF chain can connect like the one waveguide.
Okay.
Theoretically speaking.
Okay.
Yeah, yeah. So I mean, this is why I'm. So yeah, to here. Yeah. So this is much clear. So previously, if you type previous, you can see here. Yeah. Usually, yeah, one RF chain
Okay.
connect one
Okay.
like so. Because here, if you put multiple RF chains, there's no like the increase.
Advantage.
Yeah, yeah. Because this is just one. We cannot do MIMO, right? But this is yes and no because this is the previous work. But now until now, until we go this one, here we put more RF chains.
More options.
In this one, we can get more DOF.
And so what about the energy consumption with respect to classical antennas?
Yeah, I think energy, the energy consumption compared to the, so for myself, I cannot give you an accurate like number, but what I want to say is very mature. Yeah, because this is it's good energy, but I do not have a number because I'm not a hardware guy. I give you an example why, because I talked with some of my some of my friends, so of the he's like the microwave guy, so design guy, so from the Jinshus group, right? And I explained this idea, and and when he looked at my slides, he was shocked, right? And the first sentence, and he said that, so, hi Yuanwei, this is just like the leaky wave type of the antenna. So how do you make so many like slides? It's already very material our like. So in that case, I trust it's. But this is good or bad, right? Because in their like the field is already very mature, but in our it's not. Yeah, just like race. Yeah. So I have a colleague in primary. He used to heavily working on the race. His name is Hao Yang, and then our VP previous, and then I talked with research, and then he asked me, why your society still working on race? I say, what do you mean? I think he told me 20 years ago, they do this kind of things on the terminal, use this. I asked them how to do this. They do this kind of mechanical, like physically control, do this. But I explained them to him. So no, we are not physical control. We are using some electromagnetic thing to control. But for them, this is not a contribution. But for us, it's like a significant contribution. Yeah. A similar thing happens for this. Yeah.
Any more question from audience? No? Okay, so we can take a few questions from online audience. Okay.
Hi, Professor. Good afternoon. I have a small question that, if we don't have the facility to kind of fabricate the pinched antennas, do we have any kind of simulated tools to kind of, for example, reproduce your paper or something?
Sorry, can you repeat your question? Sorry. Sorry, can you repeat your question?
Yeah,
again?
yeah, yeah. I will repeat. Sorry for that.
Huh?
Yeah, if we kind of don't have any kind of fabrication facility for
Mhm.
us, the independent researchers, so do we have any simulated tools for the pinched antennas to kind of?
Fabricated. Okay. Do you mean that? The basic element for pinch antenna is waveguide and the pinch. So if you
Yeah.
do not have,
Yeah, my
think that-
question is that do we have simulator tools, simulator?
a simulator.
Yeah, yeah, yeah.
Oh, okay.
pinched
Sorry.
antennas. Yeah.
Currently, we do not have because this is very initial stage. We just do some theoretical like analysis, and to simulate. Yes, some of our colleagues ask me to do that, but I'm a bit, for me, from my perspective, I'm a bit hesitant because I'm not a hardware guy. I do need, before I do that, I need to talk a lot with how to, and I'm still worried about the modeling problem because if we have a different level of simulations, right? So for example, for my work, it's totally fine, totally correct because based on my model, right? But second one is that we need to do some channel, for example, we do some like digital twin level, right? And some, we need to do some like hardware level, right? So we need to make the real data set and also like do the channel measurements and also do the like accurate channel modeling with different models and blah, blah, something like that. And compare the, so I think this still needs some time, maybe, yeah. So that's currently we do not have the good simulator, yeah. But I don't know what kind of simulator do you mean, but if you just want to see some like our codes in the MATLAB or like the Python level, we have put it in my GitHub. You can just scan that and download the code. Yeah, you can play with that. Yeah.
Thank you so much.
So here we have a few more questions. Are pass systems mainly suitable for higher frequency bands, only like millimeter wave, sub-terahertz, or suitable for FR1 bands?
And that's a very good question. A lot of people ask me this. Yeah. Simply answer is that yes. So we can, waveguide can use a different like kind of suitable for different like frequency, but with different shape. As a picture I showed in the, so different frequency, we have the different like the shape of the like the waveguide. Yeah. But I would argue that it's better to focus on the high frequency. This is because for low frequency, we do not really rely on this kind of line side, right? So it's not that beneficial, right? But of course it's beneficial, but it's not like the apparently beneficial. But for the millimeter terahertz, because they are very sensitive to be the blockage, right? So this is more suitable for the pass. Yeah.
Yeah. Thank you for your fantastic talk. I have one questions. So you mentioned that tree pinching antenna and tree hybrid beamforming in RIS case. So which one will perform better? What is your
yeah, this is a very tricky question. How can I answer that? But I just talk from my perspective. I heavily also work on star, right? I just compare my star and pass. Is that fine, right? Because I know a lot of people are working on race. I do not want to say that. Yeah, just compare the star and the pass. So star, so it's more like the passive, right? The good thing of star is that it is, for example, this is like the whole wall and the ceiling we can put on the star. But the problem with star that is the passive, and people may argue that the energy efficiency is not that good. Right? The good thing for pass is that it is active. Right, so this is like people will not worried about the like the energy efficiency. It is more energy efficient because it is active.
but we will lose in terms of throughput and coverage.
Throughput and what?
And coverage range.
Oh yeah, coverage range, of course. But if we say that, yeah, this we reached some discussion. Of course, we can, if we want, of course we can make this kind of pass similar to a star, like this way, like the horizontal way, like this. We can make it like a star-like things, right? And I think the good thing is that it's more, but the good thing of the star is that it's more mature. because people will believe that okay, it's already there and it's already tested, and but for past people say that oh, we never see the demo, so how can I believe you, right? So this is yeah, just compare, yeah.
Yeah, thank you, Professor Yuanwei Liu. So now we have a small gift. Uh,